Today we are tackling NeetCode challenge number 002. This is a medium difficulty problem grouping anagrams. An anagram is a string made up of the same letters as another. Our task is to group all anagram into their own category. The problem statement: given an array of strings, group all anagrams together into sublists and return the groups in any order. So what is anagram? Let's define what an anagram is. An anagram contains the exact same characters as another string, just rearranged. For example, take cat and act. Both have three letters A, C, and T, just in a different order. So, cat and act are anagram of each other. Now, let's look at some examples of how to spot a matching pair. Here we have multiple strings: act, pots, tops, cat, stop, and hat. For the first string, we have act. What's the anagram of act? That is cat. How do we determine that? We count how many times each character occurs in act, and we count the same for cat. The counts match. We will cover this 26 character key in more details once we get to the implementation. So for now, our first group is act and cat. Next is pots. What are the anagram of pots? That is pots, tops, and stop. The same way, we count the characters in pots, tops, and stop. Since the counts are equal, we call them anagrams. Now let's look at the pseudocode for how this works. First, we create an empty map. Then we iterate over every string and count how many times each letter A through Z appears. That counts become our key. What is the key exactly? It's those 26 counts joined together. We then add the string to the map under that key and return all the group values from the map. So that's the pseudocode. Now let's walk through it visually. Going back to the key we discussed earlier, there are 26 letters in the alphabet and each position tracks the letters occurrence count. Take act for example. In this key, A is 1, C is 1 and T is 1. Ignoring the hash symbols for now, the raw counts looks like 1 0 1 0 0 and so on. The first position A is 1 and the third position C also 1. Further along the sequence, T is represented as 1 as well. Since act contains exactly 1A, 1C and 1T, each of those counts is 1. If a character appears twice, its count increases accordingly. So it becomes 2, 3, 4 and so on, depending on the repetition. That is essentially our key, the counts for all 26 letters, separated by hash symbols, and why we will explain shortly. For now, assume the key is simply each letter's count as its alphabet position, separated by a hash. So what's our group so far? So far, the group only contains act. Let's continue. Now, pots. Pots is different. It's not an anagram of act, so it maps to a different key. The map entries for both keys are now separate. Next is tops. Notice that pots and tops are anagrams. Their keys match because the position, count and occurrence of each character are identical. So that becomes our second group. Now comes cat. Cat joins the act group. Next is stop. Stop joins the second group. Then comes hat. Hat has no anagram among the others. It stands alone. So it forms its own separate group. At the end, we return the values, the grouped anagrams. Now, let's see how we implement this in Java. First, we create a hash map as discussed, and then we compute the character frequency for each string. In this case, the first string is act, and its frequency count is 1 for A, 1 for C, and 1 for T, generated by the loops, where we iterate over the string and compute count C minus A, incrementing it each time we encounter the character. So what does C minus A mean? A is the first letter of the alphabet and C is the character we are currently processing. The difference between them gives us the index position where we update the count. Let's check. Once the key has been generated, you can see that after finding the position and incrementing the corresponding count, we group the strings by their key as discussed earlier. Now for pods, the same way. We count its character frequencies and group it. So far, acts and pods sorted into their respective anagram groups. Continuing the same process for the remaining strings, and by the end, you will see the act and cat are grouped together. Pods and stop are grouped together, and hat is on its own. Finally, we return all the groups of strings. That gives us our list of strings. That is the Java solution. Now let's explain why we use a hash separator. Suppose one anagram has count of 1 for A and 23 for B. Simply concatenating those numbers gives us 1 to 3. Now suppose a different anagram has a count of 12 for A and 3 for B. Concatenating those also gives us 1 to 3, the exact same string, even though the underlying counts are completely different. Both anagrams would end up mapped to the same key. That's a collision, and that's exactly what we want to avoid. That's why we insert a hash as a delimiter. With a delimiter, 1 for A and 23 for B becomes 1 hash 23, and 12 for A and 3 for B becomes 12 hash 3. Two clearly different keys, so the collision no longer occurs. The root cause is that counts can be multi-digit. A delimiter keeps each number's boundary clear. Without it, different frequency patterns can collide into the same key. Now let's look at the best case. In the best case, every string is an anagram for the others. For example, cat and act are all anagrams of the same base string. So we will have just one key, and everything falls into that single group. Now, how many strings have we processed? We have processed 3 strings, and the maximum string length is 3. So we can use the max length or the average length to determine the time complexity. So what's the time complexity here? With n equals 3 and k equals 3, the complexity comes out to order of n into k. For the average case, some strings group together and some stand alone, a mixture of both. For example, bat and tab form one group, while cat, dog and got fall into separate groups. So to make this clearer, bat and tab are in one group, cat is in its own group, and dog and got are in another group. How many strings have we processed? We have processed n equal to 5 strings, which is with a max length k equals 3. The time complexity is still O order of n into k, where both n and k vary depending on the input. Worst case complexity. Now for the worst case, in the worst case, no strings are anagrams of each other. Every string gets its own group. So for every string, there will be a distinct key. Once processing completes, each string has its own unique key. We have processed 6 strings and the maximum length is 3. So this case is also order of n into